Okay, welcome everyone again to another installment of the final presentations for astronomical observational techniques and instrumentation. This is the second day, promises to be one of the best days so far. And the first speaker is Jared Wofford, who comes to us from Rochester Institute of Technology, the Center for Computational Relativity and Gravitation, and he's known as the original strange quark.
I heard that at Fermilab from the professor there. He said it's an elevator, and he just like walked out and didn't say anything else. Strange indeed. Okay, so as Professor Feiger said, I'm Jared, and I'll be doing a search of two gamma ray bursts in S6 data. So sort of a multi-messenger thing, but really two. And the two gamma ray bursts, one is a single detector, one from Livingston, and the other one is a dual detector. So we have L1 and H1, so Hanford and Livingston. So yeah, so my science question, as we should all have one, that ends in a question mark, is there a gravitational wave signal in unanalyzed S6 data that can be found using PyGRB, coherent search, which is just the pipeline, and I'll get into that. So it's a pretty bold question, but go big or go home, right? If I get it right, I get like a Nobel Prize or something. So. All right, so I like to do these things, sort of like to-do lists or questions. So this is a list of questions, and I'll go by and do like slashes through them, after we finish it and answer the question. So the first question is, what are gravitational waves? What is LIGO and how does it operate? What are some signals of gravitational waves? What are gamma ray bursts? How to analyze data? What is PyGRB and how does it handle data? And is there a gravitational wave associated with these two GRBs? And the convention is year, date, or month, and then day. Okay, so what are gravitational waves? So I'm going to try and give this talk without a lot of mathematics, almost none, because I know a lot of us haven't had statistics, and not all of us have had GR. So I'm going to try and speak fairly just in words, basically, and trying to explain things that way. So you've probably heard this 80,000 times, that gravitational waves are ripples in space-time caused by energetic interactions with very massive objects. So I put this here because we all know the analogy of a rubber sheet, and you put like a massive object on it, it moves, right? And so that's where we're going to leave what gravitational waves are. They're the ripples that are caused when you have massive objects that move and interact in space-time. And I shouldn't have to show you math because, well, I think this explains it. Give me 5 seconds. Boring, right? You don't want to see all the math. So we know they're real, so I shouldn't have to show you and explain to you that gravitational waves are real from mathematics. We observe them, so no more of this deriving and hassle. We see them and we know they're real. And so this is from the paper that was in February this year? Last year? I think it was this year. I can't remember. So anyway, yeah, it was this year. So these are the two signals in Livingston and Hanford of raw data, and well, the raw data, and then the residual noise subtracted. And this is the numerical relativity match to this data here. And Manuela showed this yesterday, and she said that it matches pretty well, and you can see that it does. And this is the frequency versus time. It makes the chirp. That's the chirp. Anyway, so we answered a question, so I'm going to get rid of it. So we know what gravitational waves are, and pretty smart. So what is LIGO and how does it operate? So what is LIGO? This is the map Manuel also showed. I stole everything from me, I swear. So this is where LIGO Hanford and Livingston are, where Geo, Virgo, and Kagra are under construction, and then planned LIGO India. So these are the gravitational wave observatories, and I'm just going to focus on these two. And not to be confused with the sardines. I don't know if they're good or not. This is all, actually LIGO is also a Russian death metal band too. Yeah, I don't know. So yeah, it's not the sardines, it's science collaboration. So this is a sort of a map of all that's in the LSC, and I want to give a shout out to the University of Mississippi right here, where my undergrad was, and then RIT's right here. It's pretty dope. So yeah, we have a lot of really, really nice institutions. It's really large collaboration, so it's really nice to be a part of. So Livingston and Hanford, I've been to both of these places. I went to Livingston, I think it's a science thing with Marco Cavalia, who is in LIGO. He was one of my professors, and we went to Livingston and hung out and listened to a lot of professors. And I did an RU, and we visited Hanford. And yeah, we walked, these are 4-kilometer arms, and we walked like maybe 2 kilometers in like 105-degree summer heat, and that's in the desert. So don't do that, it's pretty bad. Yeah, it's not good. But it was an experience. So yeah, don't try to walk to the end station. This is a bigger or more fleshed out image where you can actually see how long it is. And this is in Livingston, so you can tell it's in the swamp and not the desert. Yeah. And then this is sort of a schematic of how the interferometers are set up. So you have this laser source, and you have some mirrors here and some things that do stuff. But the idea is that you have 2 arms, and the laser hits, bounces back, and recombines here in phase, and then or out of phase, they have no signal. And these are where the interferometers are placed in the United States. And this is the strain noise versus frequency curve. So H1 L mark up there. So also Memo showed this too. This is sort of the same thing, but you get to see sort of future developments of LIGO and sort of sensitivity there. So it's pretty interesting to look at. And then there's a video. It's really small. I want to show. It's on YouTube. Sorry, guys. Is it left or is it right there? Alright, so there's no sound. So I'm a nerd for you guys. Alright, so it's going to have this laser that shoots out right here. So just wait for it. Takes a bit. It hits this beam splitter, and the laser travels down to the end mirrors, 4-kilometer long arms. You hit. Actually takes this long to travel. And then they recombine here. So when they recombine, they are out of phase, so you shouldn't get a signal at all. This is Ray Weiss, just ignore him. It's only a Nobel laureate. So after they combine, they're completely out of phase, and then you should get no signal, right? And then what happens when a gravitational wave passes is the arms stretch and compress. So they sort of shift, and you see that the 2 wave fronts are no longer completely out of phase, so you get an external signal here. So that's sort of how it works. Yeah, and they're going to show here what happens when it goes. So I think that's a very nice visualization of what's going on. And I didn't fully understand what LIGO was about until I saw this video, so that would help. So let's go back. And okay, so we saw the video. Okay. So what are some questions along the way? So we said what are some signals of gravitational waves? I think this is it. Yeah, signals of gravitational waves, sorry. So binary black holes, neutron star black hole, binary neutron stars, or cosmic strings. So that's a weird one, right? Probably not gonna happen. But you all know I really like cosmic strings, so I had to put it there. Maybe one day, I don't know. Probably not. So yeah, so now we'll cross it off. Get a little ahead of myself, so we'll cross it off. So now we know what the signals of gravitational waves are, and we know how LIGO works. So we know how to be gravitational wave astronomers, right? So we gotta look for stuff. So what are gamma ray bursts, right? So I guess we don't really know how they form. We just know sort of how they form. That they're radiation triggered from, I guess, binary mergers, and they're produced when there's like some interstellar medium, like some gas around the binary merger, and they occur roughly once per day. And they can be short or long. And I'm only going to look at the short duration bursts, which are I think 2 seconds and below. But other than that, I'm not really sure how they form, and I don't think a lot of people are even sure how they form. Except maybe Andrew's genius. So you know, put you on the spot. So we know what gamma ray bursts are. Sort of. So how do we analyze the data? So we use this. I quoted from the page because I mean, I can't really explain it any other way. So it's a tool to generate data analysis workflow, which is a way to set up how we're supposed to analyze the data using a coherent gravitational wave triggered search by short gamma ray bursts during short duration gamma ray bursts electromagnetic field freeze. So basically the idea is we send a gamma ray burst, which I know from the Fermi burst catalog, and we sort of look for data around that. And then when it's submitted, the workflow will run the pipeline to actually analyze the data coherently. So what's a coherent search? This is that a few times in there, so you may not know. So just in words, without any mathematics, I think maybe this is a really good way to put it, that we have two searches, coincident searches and coherent searches. So coincident searches will sort of add the SNR to quadrature, and they maximize over the amplitude, but in a coherent search, it adds the SNRs linearly from the detectors, and then will maximize over the sky location. And the outcome of this is that the coherent search is actually, I'm not exactly sure how much more sensitive. It'll produce the same SNR, but with lower noise, is sort of the gist of it. So let's really get into the coherent search. So the idea is that we'll have to do some match filtering, so we need a template bank, right? So generate a template bank or use one that's already there. And I'll be saying things like on source, which is 5 seconds to 1 second after, so it's like a little window, 6-second window, and then off source is just outside of that, essentially. So you can generate the template bank by weighing the waveforms with the noise that we get, just from measuring the noise outside the detector. And then the waveform actually is generated from a 3.5 post-Newtonian approximation, and assumes this mass range for your system. And also you should account for the fact that in this line here that your detectors are like not in the same location, so there will be some signal that reaches here at some time, and then sometime later it'll reach here because light isn't instantaneous, so it takes time. And so then they're combined to form the coherent SNR, and then the data will get read in and split into frequency bands, and each template is filtered against this data. And then a trigger is recorded anytime the coherent SNR that's calculated is greater than 6, and no ladder event occurred in any template within 0.1 seconds. But it's just so we talked a lot about noise in this class. So the noise of this detector. So we have some data, and then we have this Gaussian noise component here, and this template waveform right here by some amplitude, and then the non-Gaussian noise component by this amplitude here. So that could be something like glitches or stuff, which I'm also going to talk about. So the idea is that how do we get the signal, right? So I'll explain that. So there's a few steps to how to get this signal. One of them is doing this amplitude consistency test. So it's plotting your single detector SNR versus the coherent SNR. And so there's a cut right here at SNR equals 4, and that just gets rid of all this crap here. And that's vetoed, so it gets rid of it. And then there are triggers that form like this from these glitches, this blue line here, that have a really large coherent SNR, but it's negligible here for each one, so just get rid of that too. So the next thing we do, so that gets rid of some noise. The next thing we do is more veto cuts. So the first thing is bank veto. So this is the distribution of bank, the chi-squared bank versus or frequency versus chi-squared bank. So the idea here is that you're going to perform a chi-squared test here, and then the motivation behind this is that that glitches will have power to match with the template you have, right? So you'll have a peak in SNR, but it's not actually a signal, right? Because it means it's a glitch. So it'll make your SNR increase, but it won't actually be the gravitational wave signal. So we should get rid of it essentially. So that's what this chi-squared test does. And this line here is what we do, and you get rid of everything above this, right? So you're left with this here. So we got rid of some more triggers. And we're gonna do another one called the auto veto. It's like, I don't know if you've heard of autocorrelation, but it's sort of the idea there is that match filtering says that there's a peak in SNR when you hit a template, but maybe they're offset by some amount, right? And so this noise transient will sort of make the SNR peak, but it will sort of not have the same signal as a gravitational waveform. And so this essentially just tests the consistency of this peak in SNR, and you make another chi-square test and you get rid of this stuff again. So that's really nice, and then you see that left is a lot less. And then the last one is a chi-square test. It generates something called the new SNR, which is a new data statistic. And so that is essentially used to tell you whether you get a detection or not. So, and this essentially just downweights the significance of the noise triggers. So, yeah, and then these dashed lines are of SNR. I actually don't remember what the dashed lines are. So I think, these are equivalent. So if you have a signal, so if you have a trigger here, it's equivalent to having the same SNR here. So they're sort of like contour plots, I guess, or equal potential lines, something like that. I think is the way to explain it. But yeah, so we can cut more bits of the data out there, and then we can, like I said, make this detection statistic, which is essentially the new SNR. This peak here. And then we can also form what's called a false alarm probability, which is this fraction here, which is based off P. And then you can make this sort of efficiency plot. So this plot here is, so the black line is the trigger versus, the amount of triggers versus the loudest background event, this black line here. In the Gaussian noise, and then the red dashed line is the lowest amount there, and in real noise. And then the blue line here and the green line here, the blue line is the signal amplitude, the amount of triggers versus signal amplitude. Oh no, sorry, it's the detection. It's the efficiency calculated from the detection statistic here. So yeah, that's what these in real noise and then in Gaussian noise. So yeah, so we have two ways to do it: one in real noise, one without Gaussian noise, and then two ways. So detection statistic not. So we're done with that sort of I guess background. So last thing is, do we have gravitational waves? So everything I just explained, I'm going to go through again with actual stuff I did. So actually, the plots I just showed were from a paper outlining the process, and I'm actually going to show how to do that. So the S6 data, science run 6, I actually didn't know what S6 meant for the longest time, but it's pretty simple. So it occurred from July 2009 to October 2010. And it's data that hasn't, and I'm going to use data that hasn't been analyzed, except for one. I thought it was previously unanalyzed, but unfortunately it actually had been done, but it's a good exercise. And then there's one single detector, GRB, that hasn't been done, and it may have a really interesting result. So, and like I said, I got it from the Fermi burst catalog, and then the two sources here. So, single interferometer source and then the H1L1 source. So, this is the first one. Don't memorize the number unless you have to find a folder. Okay, so this is the sine segments. So we see here the on source and then the off source, right? So this is where we think, this is where like p equals 0. This is where we sort of think the signal may occur. So so we take out the t equals 0 and just work with the outside data here. So it's pretty noisy. Yeah, we have some things up here. So yeah, and this is H1 and L1, so it's not super good, but we're gonna work with it anyway. And this is the coherent SNR, like I said, it's calculated. So we have some more stuff here, and yeah, not super good, but we're gonna do these tests. I just did the bank veto. So when we made this chi-square test and then the bank veto would cut everything above it, that's what we do here. So as it says, the blue crosses are the background triggers, a lot of the stuff, and then the red crosses are the injection triggers, and then the black line is the veto line, and then the yellow lines are the contours of the new SNR. So contour plot was the right thing to say there. So yeah, and then we'll do the auto veto, sort of the same thing here, get rid of more crap, and yeah. Okay, and then the chi-squared veto, again, is sort of the same thing, getting rid of more data. So you're left with the sort of pocket here and these triggers here. So we can take this and say this is the, make these single detector plots that I showed. And we see that here was the cutoff line here, so everything below that goes away, same with H1. And then the green line is the expected, these green lines here, the expected SNR for the injections, these red crosses. And then the magenta and cyan lines are the 1 and 2 sigma errors on that. So yeah, it's just some data filtering. And then you end up with this new SNR here, and there's still this at 0 missing here. So look at it. So you run a shell script called open the box, which I thought was really funny. And you fill in this data, and you would hope to see a gravitational wave signal here. But I mean, can you guys see it? No, it's not there. So yeah, it's not there. So even if it was something here, like, it'd be pretty hard to tell, like, versus this. I mean, yeah, it's not very good. And then fill it in here too as well. So you see H1 and L1 here. So it's not very good. So, and then the coherent. So I didn't find a gravitational wave. That was pretty lame, right? But I can say some things about it. So I can do these confidence intervals here. So if we make these efficiency plots, right, and then we can say that with 90% confidence that there's no neutron star within this many parsecs, and 50% is this many parsecs. So we didn't detect one, right? But we can say there's not one. It's the same, right? I get a Nobel Prize. But, so yeah, I mean that's pretty nice to say though. I mean you can sort of say some things about the universe that there's not one here. So and the same thing for neutron star black hole. So 15, 17. So that's here, right here, here, here. And this is sorry, I also forgot to mention that these plots here. So this is versus the background, the lattice trigger in the background versus, and this is versus the lattice trigger in the foreground. So that's why there's 2 plots there. But so there's not one there. It's not cool, right? So we're going to do one with a single detector, which previously hasn't been done because you couldn't do it. So we're running a new code to do this. So just over L1. So here there's no data here. It's at 0. So we have this data and it's sort of noisy. So yeah. And then can we guess what the coherent SNR is? Isn't it the same, right? Because there's one detector. So it's the same plot. But yeah. So I'll run more of these tests. This is the bank veto again, right? So we get rid of all of these, which is pretty nice and stuff. These left, it's again, sort of all that crap. It's garbage. Don't need it. And then here, we got rid of a lot of it, so we're left with this. And can plot this new SNR here. Still nothing at 0, right? So if there's a gravitational wave, you should expect to see something at 0, like a peak, right? So you think we'll find one? Nobody? Nobody has faith in me. Well, I did. Just kidding, just kidding. It certainly looks like there's a signal there, right? If only. So there's not a signal there, so I'll spoil the fun. It looks like there is. Get really excited for like 2 seconds and you're really down. So yeah, making these plots, this is the new SNR. Seriously, it does look like there's a signal there, so there's something happening, right? So there's something happening at Livingston. So what's happening at Livingston? So maybe there's like an alligator like crawling on the detector. I guess that happens in Louisiana a lot. LSU played a really loud football game, I don't know. But something happened, so in these channels, you can sort of run like a noise analysis called an omega scan and see what sort of glitches were happening in the channels. So these are some channels, and you can see that these red spots are definitely not gravitational waves. But yeah, I don't know what happens there. But the funny thing is, if you're thinking it's seismic noise, like there was an earthquake, actually it wasn't, because in the seismic channels there's nothing there. So I'm not sure. Maybe actually best guess maybe like a misalignment of a beam. I'm not really sure. I don't really work with glitches. So yeah, so I didn't find one, but I mean, I almost did, right? I found a glitch, which happens a lot, but I can still say some things about the confidence levels of where we can find binary neutron stars. In 90% confidence level, 11 megaparsecs, and then for 50% confidence level, 17. And then same thing for black hole neutron star. Or sorry, this is neutron star, and then 17. So we answered all my questions. So it's nice to see that we went through and answered all these questions. So you should all be experts on all of this by now, and should be able to find the gravitational wave like I didn't. But so here's my science question. We'll go back to it. So is there a gravitational wave signal in unanalyzed S6 data that can be found using Pi-0b? No. Reluctantly. Maybe. So yeah, I want to say a huge thank you to Andrew. He helped me a lot and answered a lot of really stupid questions. So yeah, really thank you. And then have some XKCD. Like 25. Okay, questions?
For the strange quirk? Yep.
Yeah.
So you have your on source and your off source.
Yeah.
How do you decide what your off source is? Like,
So-
is that arbitrary time around it, or?
Yeah, so I think it's chosen to be, what, 2,000-ish seconds? Well, 2,000 seconds as in GPS time. But so let's go back. So here, yeah, so on source. Actually, this is the off source. This yellow line here is the on. Yeah, it's chosen pretty arbitrarily. You want to look, so it's like short, so short gamma ray bursts are formed from the verges, right? And so that's a very short time scale. So you want, we know that the time scale should be like those 6 seconds before and after, and so that's what we picked for that. And you want the noise from outside of that, so you want to sort of make sure you know the background of what's going on there. So yeah, so I think the off source is, to my knowledge, is pretty arbitrary, but maybe that's not true.
More questions?
When you did this particular search, were you not using the Hanford one just because it wasn't operating at the same time
Yeah,
for that particular signal?
it's not there.
Okay, so it was just something.
But I also did want single interferometer GRPs. So
Mhm.
I wanted to run over that because that's not been done.
How would you find a signal if you can't corroborate that it's not? I mean, is this noise analysis sensitive enough that you can just say?
Just have like
certainty?
one, just have one.
Because I always thought that's how they detected them, was between the two, they could just rule out everything else.
Yeah. So I'm not really sure. To me, it seems like you should definitely have two because like it's like if you have like a signal in one and you don't have the signal in the other, obviously there wasn't one, right?
Mm.
If you have two signals that are the same, it's coincidence, right? You should get the same thing, but you'll be able to tell that if they have sort of the same signal with the offset, there's something there you should look at. With one, I'm not really sure. I'm sure you'd have to have sort of a larger like confidence value or a larger detection statistic for that. So, but I'm not sure of the threshold. What that is. Pretty large. So. Yeah.
If there was a detection, what information could you get from this data?
What can I?
So what could you know about the
what can I know about it?
projects that?
Well, so it was run over sort of the span of like 1 to 40 solar masses. I still have this question of how, if you know the waveform, you should be able to figure out something about the system. You should be able to figure out the masses and how far away it is. But to my knowledge, I'm still not sure how you should be able to figure out. I guess from the frequency, you should know how fast they're going, and I guess from that, you should be able to get. Actually, from the gamma ray burst, you should be able to get the distance, and then you should be able to get the masses from that. But I'm not sure how the relative is different. So no one's ever taught me. But you should be able to theoretically get that. I mean, if you read the LIGO paper, they put bounds on the masses for that. I think it's like 30 cube or something. So yeah.
Is that it? Those are all the questions I have. A few. Any more? Let's see. Could you go back to 7?
7. And it's 64 slides. That's a lot.
Well, it was the animation, the nice, I think it was
The animation?
I think it was the video, it was showing the arms that were stretching,
Yeah.
both arms, so I guess you don't really have to go back to it, but.
I mean, I can.
Can you tell the direction of the object by looking at the relative amplitude in the two arms?
Yeah, you can triangulate the signal, but I don't think it's very sensitive. It's not like you can pinpoint like, oh, this
But is it the case that the signal can only be in one arm?
It can only be in one arm?
Is it possible that the signal could only be in one arm if it's orthogonal to that arm, the direction of propagation?
Yeah, I see what you're saying. So this is why we have two detectors that have two orthogonal directions. Let me show you the.
So I am thinking about it the right way, that it's like an electromagnetic wave in a sense, and it's perturbing these two arms.
Yeah, so like the plot I think my computer stopped, but the plot I had here that showed, it had the map of the United States, it had Livingston here and Hanford here. The paper had this plot specifically to show the two orthogonal directions of the interferometers because of that. So.
Yeah, okay. You mentioned, I think you said the word injection, I'm not sure you defined it.
Injection?
Yeah, what is that?
So it's injection is like a signal from the template bank put into the data.
It's a false signal?
Yeah. It's a false
Okay. In some of your plots where you had SNR, I believe, this is an S6, the S6 data.
Okay.
I don't have the slide number, unfortunately.
Okay.
But you showed quite a few plots,
Yeah.
SNR versus something. Yeah. So what are all those vertical structures?
This stuff here?
Yeah, what are all those things?
Yeah, glitches. Glitches. Well, maybe glitches, just noise probably. Glitches or noise. I actually don't know unless I did a search.
But they look very non-Gaussian. It looks like
Yeah.
some sort of at a fixed frequency or something.
Mm-hmm. Yeah. Yeah, it could be just noise or glitches. I don't really actually know that much about glitch classification, but I know there's a lot of glitches, like the one you saw here that happens. And I texted a friend who knows a little bit about this, and he saw the plot and he was like, pesky, whatever this glitch is number. And I was like, how did you know that? And he says it just happens.
Yeah. So the zero there, does that correspond to a GRB event?
Yes.
Okay. That was another one of my questions. I think you said you ruled out that there's an event in the time window that you examined, I guess.
Yes.
That there's no event.
There's no event.
But it looked like there was a funny thing there, and you concluded that probably pretty quickly. Yeah, you concluded probably pretty quickly that that's not a gravitational wave.
The detection statistic was not above the threshold for that. So. And then you can run this this sort of, they call it a megascan, and you'll see what's going on in the channels, and this is obviously not the gravitational wave signal, right? We solved the chirp, but I mean that's obviously not a chirp. It looks like somebody banged on the detector.
And can you repeat? I think you said this, but I just wanted to say it again. The science implication for not finding an event is it easy to say?
The implication for not finding it?
Yeah.
So I'm not sure if I understand the question. So I haven't found an event, but we can say with a certain confidence level that there is an event in this sort of range. That's
This is for a specific GRB event. You didn't find a gravitational wave. So can you make a statement, a science conclusion? For instance, you could say, clearly for this GRB event, it was not the case that two massive black holes coalesced.
Right. Yeah, I mean, the detection statistic didn't cross the threshold, so you know that there was an actual gravitational wave, so of course there was no merger, right?
Could there have been a merger just to smaller masses?
I'm actually not sure. I assume not, because I set the threshold for the binary system to be one solar mass of like 40.
So with the noise characteristics, you could have detected
Oh, you're saying it could be like buried in the noise?
I don't know, I'm wondering what the science implication is. It seems to me you should be able to say something like, for this event, it's clear that the following things didn't happen.
Right, okay. Yeah. So I'm not sure. All I can say is I have not detected one. I don't want to make broad statements.
Yeah,
about
so
what
that might be interesting to be able to extend the null result to a statement about
Right.
certainly didn't happen, because then you could put limits on the GRB phenomenon. you can say, well, at least in this one case, this person published this
Sure.
non-result, and it's clear that, or at least in that case, it wasn't,
Yes.
Is that what you can say, that it didn't happen, or is it just it didn't happen within this distance? Because if it was close enough.
yeah,
then-
so I purposely didn't cover the multi-dimensional phase space.
Alright.
But one dimension is distance, right?
Yeah.
And so your statement, so it's difficult to make a simple statement the way I said it, but you could imagine making a plot of multi-dimensional phase space and then excluding a region of the plot.
Well, that's what the curves are, but that's what.
With the contours.
That's what that is.
Oh, those things.
You inject simulated signals and see if you find them lighter than your background.
Okay. Any other questions, comments? That's it. Okay, let's thank Jared.